Consider the following format of 3 address instruction with 4-bit opcode and 3 4-bit addresses. So opcode followed by address 1, address 2 and address 3. This is the format. If there are 15 such 3 address instructions, then using expanding opcode technique, how many maximum 2 address instructions can be encoded? So here the format is given as opcode followed by 3 address 1, address 2 and address 3. So the number of bits given in the opcode is 4 here, and also address bits are also 4 bits. Address 1 4 bits, address 2, address 3, like that. We need to find out using expanding opcode technique how many 2 address instructions can be encoded. Already given that 15 3 address instructions are there. So using 4-bit opcode, the maximum number of operations you can perform is 2 power 4. That is 16 operations, out of which 15 is already used. That means there may be something like 00, 002, 1111. These codes are possible opcodes. But 15 means that is 00002, 1110. Up to this it is already used. So the last one may not be used. Only one opcode is available for using. But we can expand the opcode. For 2 address instruction, out of these 3 addresses, one address can be used as the opcode bits, so that we can expand that opcode by using a part of the address. So number of bits in address is 4. So the maximum number of combinations, this one opcode availability into 2 power 4, because there are 4 bits in address. Remaining 2 addresses we will use for the 2 address instructions. So that 1 into 2 power 4 number of 2 address instructions are possible, that is 16. Option C is the correct option here. A floating point number can be represented as plus or minus 1 point m into b power e, where m is a mantissa, e is exponent, b is a base, that is also called as a radix of the exponent. So the format is like this: s, e and m. So the mantissa is occupying 23 bits from 0 to 22, and from 23 to 30 these 8 bits are meant for exponent, and 1 bit it is a sign bit. It is whether it is positive or negative, it represents. The given figure represents a floating point number having m is equal to 23 bits, e is equal to 8 bits, and s is the 1 bit sign. Assuming b is equal to 2, that means it's a binary system. If 1.75 base 10 is to be represented in the above format, then what will be stored as e? So what will be the exponent? We need to find out the exponent of this. So now bias is equal to 2 power e minus 1 and representation is normalized. So we can represent a 1.17 like this in binary. This is the fraction part and 1 is the integer part. It is given in decimal format, so that we can represent like 1.11 into 2 power 0. So bias is equal to here 2 power e minus 1 minus 1. So that means it will be 127. So this 127 can be represented like 0, 1, 1, 1, 1, 1, 1, 1. This is the base 2 in a normalized format. So option C is the correct option here.
Here in this question, R is a relation R is a relation from A to A, and set A is given as 1, 2, 3, 4, 5 and 6, and few elements in relation R are given, and we have to find the minimum number of elements to be added in R to make it an equivalence relation. In order to solve this problem, first of all we have to know what is equivalence relation. A relation is equivalence if it is reflexive, transitive, reflexive, symmetric, and also transitive. So what is reflexive? X relates to X for all x belongs to A. That means for all the elements x in A, x should relate to x. Then only it is reflexive and symmetric. If x relates to y, then y should also relate to x. This is called symmetric. And what is transitive? If x relates to y and y relates to z, then x should relate to z. This is transitive. Here R is given as R consists of elements like 1 2 1, 1 2 3, 1 2 3, 3 2 1, 2 2 2, 3 2 3, 4 2 4, and 5 2 5. Here it is given that R should be reflexive. R should be equivalence. So it should be reflexive. For reflexive, 1 to 1, 2 to 2, 3 to 3, 4 to 4, 5 to 5, and also 6 to 6 should be there. So here 6 to 6 is missing. So if we will add 6 to 6. So let us check. After adding, let us check if this satisfies the remaining two properties. So here R should be also symmetric. So here 1 to 3 is there. 3 to 1 should be there, and 3 to 1 is also there. So again, it should also satisfy transitive property. Here 1 to 3 is there, 3 to 1 is there. So 1 to 1 should also be there. Here 1 to 1 is also there. So we can say by adding 6 comma 6, R will become equivalence relation. So here the minimum number of elements should to be added is only 1. So here correct option is option A.